Hey everyone, so this is going to be a bit of a review on what exactly equilibrium is, right? Because it's really important just to understand that concept. And then we're going to be kind of going over how to plug into the equilibrium constant formula. That part is not so much difficult to understand as it is just being able to do it essentially. So first, again, we have to remember that there's a such thing as a reversible reaction, right? A double arrowed reaction. And most reactions are that way actually. It's kind of complicated, so we haven't talked about it till now, but most reactions in chemistry are reversible, where most times we talk about reactants going to products, but it is also possible for those products to revert back to reactants. That's also a possibility. So we represent this with a double arrow. Here's an example of a reversible reaction, right? We're heating up this copper 2 sulfate pentahydrate is the name of the blue stuff. And when it's heated, right, the endothermic process where heat's being supplied, it will then convert into anhydrous copper sulfate. The water will have been cooked out. And then if we add water back in, that's actually an exothermic process where it turns back to the blue crystals. So this is a reversible reaction. We see it changing into one and then having water added, converting back to the other. So that's reversible. And then we want to be aware of a very important aspect of reversible reactions, that is that a reversible reaction will typically eventually reach equilibrium, right? So, for example, if you have a closed water bottle, this will happen in there as well. And this isn't a chemical reaction so much, but this is still an equilibrium process, where if you have a closed water bottle, here's sort of a zoomed in view of what's happening to the molecules, but this is still happening even in your home. We know that some of those water particles are evaporating, right? But at the same time, when you stare at it, nothing appears to be happening, A, because it's slow, right? But also because at the same time that some of those particles are vaporizing, right? Because then you're like, well, then why doesn't the liquid level go down? At the same time that some of those particles are turning to vapor, at an equal rate, other particles are going from water vapor to liquid. And so this happens all the time in equilibrium, where if you look at it, it looks like nothing's happening. But if you really were to zoom in, you would see that there's switching, like it's all happening in a cycle so fast that it looks like nothing's happening. So if equilibrium is reached, there's no visible change really, because there's a cycle occurring where they're changing. Equal amounts of particles are condensing as there are particles that are vaporizing, if that makes sense. So, but we could also have, like, let's say your water bottle had like a very, very little bit of water at the bottom, and then like there were a lot more particles of water that were gas. The equal in equilibrium, as a reminder, does not stand for being equal amounts of both. It means the rate back and forth is equal. So you could have like a ton of water vapor and only a little bit of water liquid at the bottom, and you would still have equilibrium as long as the rate at which the water was vaporizing was equal to the rate at which the gas was condensing into water. It's about the rate. It's not about how much you have. Okay. So this is just a reminder of visualizing that. Initially, and this is going to be important in a minute, initially when you have any kind of setup for equilibrium, we just have the regular reversible reaction occur. So right now we're certainly not at equilibrium. The initial reactant you have starts to convert to the product. So those are all changing over. And then we start to see sort of a back and forth happening. Well, then some product will return and become reactant as this is progressing. And we're not yet at equilibrium yet, but we are seeing a change back and forth. And we're still changing back and forth. That time we had 8 go from green to blue, and then 6 go from blue to green. And then now we're seeing equal amounts of both change. So that's when we're at equilibrium. But we are noticing at the end of equilibrium, we have 13 particles of green and 27 particles of blue. It's not about the amounts, it's about the rate. If we were to keep doing this over and over again, we would see no change over here, because 7 would go from A to B and 7 would go from B to A. There's still a lot happening, but it looks like nothing's happening pretty much if you've reached equilibrium. And the equal in equilibrium is about the rate being the same. Okay, so we're going to see some of that later. This is showing that too, right? The rate at which A and B are reacting to form AB is the same as the rate at which AB is splitting to form A plus B. That's all that we're saying here, no change. So equilibrium is a state in which there is no observable changes as time goes by. It's achieved when the rates of forward and reverse reactions are equal and the concentrations of reactants and products remain constant. So not that they're equal to each other, but the reactant concentration is not changing and the product concentration is not changing because the rates back and forth are equal. So it looks like, again, nothing is occurring. We saw that with H2O and gaseous H2O, but chemical equilibrium is specifically when you're changing chemicals, not just state of matter. And that's the one we're really focused on here. Okay, so here's a great example, N2O4 going to 2N2O. These are two entirely different chemicals, right? So this is a chemical reaction, reversible. And we see in the first one, right, we've got a lot of NO2 and no N2O4. This is sort of like we looked at a minute ago, where we had all A and no B yet, which is very possible. This happens all the time with equilibrium. You could have all of one reactant and then none of the product yet. And then we see as time goes on, we're not yet at equilibrium, but we're seeing that the product amount is growing as NO2 converts into N2O4, right, as the red, in this case, goes to green. And they're switching back and forth, until eventually they both flatline. As they're flatlined, that's equilibrium, because we're seeing no change in both of those. We're seeing the same thing. It's remaining constant. Over here, we're actually seeing the opposite occurring, where we initially have a ton of N2O4 and not really any NO2. And then as time goes on, we're seeing them both transform into each other until eventually we reach a flat line for both. And notice we don't have equal amounts of both, right? We're at different parts. Concentration is not the same for each, but there's no change occurring eventually between them. Now, again, important to note that for all of these, NO2 and N2O4 are still transforming into each other, even when we get to the flatline part. So you can sort of imagine this is going to that, and this and that's going to this, back and forth. But we're not seeing any observable changes because the rate has equalized. Finally, in this case, we see we've got some of each that we're starting with, right? We're neither started at 0, which is this bottom left corner. We've got some of NO2 and some of N2O4, and even still, they will reach equilibrium at some point. So what we're noticing is that eventually we will reach equilibrium in a reversible reaction. It will happen. And let's look at some of the data for this. So equilibrium, that's when it's occurring. Okay, now in every situation, right, we've got different amounts of initial concentrations. Equilibrium concentrations are also different, right? But what does hold constant is the ratio of products to reactants. So even though in every situation we did stop at a different concentration of the products and a different concentration of the reactants, see we're stopping at different points here for each of these situations. When we look at the actual raw numbers, the rate of one over the other when we set up this equation properly is actually constant. It's the products over the reactants. If we take products in the numerator over reactants in the denominator and we set up the formula correctly, we've developed a formula that shows that the ratio is actually a constant. So that number holds still pretty much. It's just about the same regardless. So we need to be able to set up this equation for this constant. And the rules are not actually all that bad. It looks a little funky, but it's just takes some getting used to. First thing is, this is our generic equation over here. And pretty much all that you do is, first of all, you write K, as in the constant, is equal to, some of the web assignment actually requires this, and then you do products over reactants. So that's another important piece, is doing products over reactants. And then the last piece of that is you're going to put them in brackets to show their concentrations. The brackets mean concentrations, or in terms of gases, they could mean pressure. Those are the things that could change in an equilibrium setup, right? Some gases will be switching between each other, changing the pressure of the system. And then some chemicals will just be changing concentrations. And typically that's in molarity, which is why we did molarity last unit, just as a sort of a lead up to this. But anyway, the setup, products over reactants. And even as you're watching this, I would literally like say this out loud to yourself or mouth it out loud to yourself, because I always want to remember that part. And then the other change up is that the coefficients of the reactants and products actually become an exponent. So that's a little bit strange. So if we look at, in this example, this equation was first balanced, that's important, and then we did products over reactants, but this 2 coefficient became the exponent of the chemical. So we're saying like the pressure, for example, actually we're looking at concentration. The concentration of NO2 squared over the concentration of N2O4, which had no coefficient, so no exponent here, is equal to some constant. Now you're not expected to know that constant. That'll be something we either calculate because you're given the rest of this information, or in other situations you'll be given that constant and you'll be given the concentration of one of these and have to find the other. It's the typical scenario, right, where you're given an equation and we'll give you most of the information, you got to find the last part type thing. There's going to be no situation where you have like several variables. Well, never mind, we'll get to that a little bit later. But that's the idea. Products over reactants, coefficients become exponents. That's the broad idea. Okay. Now, generally speaking, if when you solve for this, the K value is greater than 1, right? That means, if you think about what that means for a minute, if the fraction is greater than 1, that means that the numerator must have been greater than the denominator. And if we take that a step further, that means that the products at equilibrium, right? Because we're talking about once we've reached equilibrium here only, at equilibrium, the concentration of the products must have been higher than that of the reactants, which isn't always the case, but this is just a possible situation. So again, greater than 1 means your fraction was greater than 1. Numerator was greater than the denominator, which means that your products were favored. And we say that products were favored. There's more essentially products made. The equilibrium is said to lie to the right, or in other words, our products are shown on the right, right? So we're saying that at equilibrium, we've actually got more products at that time. And we say that favors products, or pretty much you have more products in that situation. Okay, and then alternatively, if K is less than 1, then we're saying that the denominator must be larger than the numerator, right? So that means that at equilibrium, because that's the only time that we use this equation, at equilibrium, that means that the reactants at that time must have actually been more than the products, which can happen, right? Because all equilibrium means is that the rate back and forth is equal. It says nothing about how much of each thing you have, so it's quite possible that once you reach equilibrium, you've actually got more reactants than you do products in a reversible reaction. So that is said to lie to the left, or in other words, we favor the reactants. The reactants are more concentrated in the end at equilibrium. Okay, so let's look at first the homogeneous equilibrium. This is going to show you how to set up this equation. So first thing, again, in this case, H2O is going to be constant. So when you have a pure liquid, we don't count in the equilibrium expression, right? So that's one of the rules. If you have a pure liquid, we don't count in the equilibrium expression. If we look at this, it makes sense because the liquid itself doesn't really contribute overall to what's happening. It's more so the other chemicals. We also consider, because if you think about when something is dissolved, usually there's like way more solvent, right? So that solvent amount is considered to be so much greater than the rest of the chemicals that we're not going to consider it essentially. So a pure liquid, letter L, don't put it in the equation. So our Kc, or our equilibrium constant, right? Some constant value that our equilibrium always reaches for that particular equilibrium, is going to be products over reactants, right? So we've got our right side chemicals, this one over here, and H3O plus on the top, and then our left side chemicals, excluding that pure water, that liquid water, not included there. I forgot to mention this before, but an equilibrium constant at a given temperature will always be the same for a certain reversible reaction. It's a constant. No matter what, it will be the same at that temperature. That's the only thing that can actually change it is temperature. It's the only thing that will affect the equilibrium constant. So it should be roughly the same number for each reaction, no matter how much you start with or how much reactant you start with, how much product you start with. We saw earlier that it's a constant. It's the ratio of products to reactants at equilibrium. So we can start with a ton of either, and eventually we'll reach equilibrium, and then the ratio of the two will actually be the same when we finish. But okay, so this is our setup. In this case, we didn't actually have any coefficients, so yeah, we didn't include them. And again, it's products over reactants. We do not include, we also don't include units typically for this because we're considering units to be canceling out. We got the same units on top, same units roughly on bottom, technically not, but for us, we're going to say no units, unitless quantity. All right, a heterogeneous equilibrium. So in other words, we have mixed states occurring. We didn't just have, like in that case, we had a homogeneous equilibrium, liquids and aqueous. In this case, heterogeneous is meaning different things, different phases. So we've got calcium carbonate solid is going to become calcium carbonate and CO2, and that's going to eventually reach equilibrium. Got solid gas. Again, we do products over reactants, but in this case, we don't ever count the solids. So if you're kind of writing this down, don't count liquids, don't count solids. We don't count the pure things. We only count the we don't count the pure liquids, pure solids, I should say. We just count the gases and the aqueous. Those are the only things that go in. So that's literally our whole expression. Kc equals the concentration of CO2, or Kp, if we're talking pressure, is the pressure of the CO2. The concentration of solids and pure liquids are not included in the expression of equilibrium constant. So skip over those things. Here's sort of a visual of why that is. If we're considering, for example, the pressure changes caused by CO2, then we're really focusing on CO2, right? Solid calcium carbonate and solid calcium oxide are not really going to contribute so much to that pressure. They don't take up much space anyway. So that's sort of like a broad idea of why we do that. PaCO2 does not depend on the amount of calcium carbonate or the calcium oxide. So the pressure of the CO2. Okay, here's a problem we'll do together. I recommend having your notes out for this because I didn't put this work in your notes. Equilibrium constant Kp for the reaction is 105 at 1000 K. So again, the only reason they're telling us that is because the only thing that changes equilibrium constants is temperature. So in the problem, they usually specify a temperature. It's not actually going to be part of your math at all. They're just saying, at this temperature, this is what the constant is. At other temperatures, it'll change. So they just have to specify, but it doesn't factor into the math at all. What is the equilibrium pressure of O2 if the P of NO2 is 0.4 atm and the P of NO is 0.270 atm? Okay, so let's see. It's giving us the equilibrium pressures. So first thing you do before anything, do not just jump right into this. The first thing you do is set up your generic. This is so important. Set up your generic equation, then you'll set yourself up for success. And for those of you who don't write it out, I'm telling you, it's going to come back to bite you terribly in this one. This one is going to be really hard to do mentally. So products over reactants. The pressure of NO, this is saying squared. That's a little funky because there's a 2 coefficient in NO. And the P of O2, no exponent because there's no number in front. And then products over reactants, so the reactant is the P and O2, and that's squared. So we set up our generic, that's set up like that, move things around, set up the equation. So what they did actually was they're trying to find the PO2, pressure of the O2. So they kind of isolated that from the equation. It's recommended you kind of manipulate the algebra first. So if we're trying to get O2 by itself, we would essentially be, I would pretty much just manipulate the algebra to get there. This is the result of moving things around and isolating PO2 first. But then we go to put things in. This is just showing that our constant was 158. So that's Kp. That got put in right there. And then our P of our pressure of NO2 was 0.4 atm. And that value is squared because just like we squared it in our setup. And then finally at the bottom, our pressure of NO at equilibrium was 0.270. So then we square that too because that was how we wrote it because of our 2 in front of it. So once you set it up, it's pretty much just solving just like normal for a variable. Really, the question is, did you take your time and set it up properly? Easy to make mistakes on this kind. And then the answer at the end is 347 atm. So in other words, at equilibrium, the pressure of oxygen gas will be that much, which is pretty significant actually. But that's what it would be. Okay, this is our last piece. So the concentrations of the reacting species in the condensed phase are expressed in molarity, capital M. In the gaseous phase, the concentrations can be expressed in molarity or in atm. Condensed phases is in pretty much not gases. I don't know why we have to make it so complicated. Yeah, if we're talking about other things besides gases, we're going to use molarity. And if we're talking about gases, we're going to use molarity or atm, depending. The concentrations of pure solids, pure liquids, and solvents do not appear in the equilibrium expression. Exclude them. They don't count. And the equilibrium constant is dimensionless. This is our summary. And then in quoting the value of the equilibrium constant, you must specify the balance equation and the temperature. Again, the only thing that changes in equilibrium constant is what temperature the situation is at. So that's why questions express it. You don't actually use it in your math, but you do need to say in your final answer, the equilibrium constant K is this at this temperature. Because at any given temperature, it'll change. So that's a pretty significant thing. There are any number of numbers it could be for every temperature change, so you need to specify temperature. Okay, and that's it for now. Thanks for watching. Again, reach out with questions. This is one of those things, I know it was 20 minutes, sorry for the length, but I recommend, slowing it down, really digesting everything. Main thing, products over reactants, exclude solids and pure liquids, and coefficients in the balanced equation become exponents in the expression. So this is one of those things that's new, but it's not, I don't think it's all that hard so far. It's more just like new. New requires studying so that when it does get hard, which it's going to get a little bit hard, you can do this part pretty much. Okay. Let me know if you need anything.